This article aims to be an accessible introduction. For the mathematical definition, see decimal representation. The decimal numeral system has 10 as its base. It is the numerical base most widely used by modern civilizations. Decimal notation often refers to a base 10 positional notation such as the Hindu-Arabic numeral system or rod calculus. However, it can also be used more generally to refer to non-positional systems such as Roman or Chinese numerals, which are also based on powers of 10. A decimal number, or just decimal, refers to any number written in decimal notation, although it is more commonly used to refer to numbers that have a fractional part separated from the integer part with a decimal separator. A decimal may be a terminating decimal, which has a finite fractional part, a repeating decimal, which has an infinite fractional part made up of a repeating sequence of digits, or an infinite decimal, which has a fractional part that neither terminates nor has an infinitely repeating pattern. Decimal fractions have terminating decimal representations and other fractions have repeating decimal representations, whereas irrational numbers have infinite non-repeating decimal representations. Decimal notation. Decimal notation is the writing of numbers in a base 10 numeral system. Examples are Brahma numerals, Greek numerals, Hebrew numerals, Roman numerals, and Chinese numerals, as well as the Hindu-Arabic numerals used by speakers of many European languages. Roman numerals have symbols for the decimal powers and secondary symbols for half these values. Brahma numerals have symbols for the 9 numbers chapters 1 to 9, the 9 decades 10 to 90, plus a symbol for 100 and another for 1000. Chinese numerals have symbols for 1 to 9, and additional symbols for powers of 10, which in modern usage reach 1072. However, when people who use Hindu-Arabic numerals speak of decimal notation, they often mean not just decimal numeration, as above, but also decimal fractions, all conveyed as part of a positional system. Positional decimal systems include a zero and use symbols for the 10 values to represent any number, no matter how large or how small. These digits are often used with a decimal separator which indicates the start of a fractional part. Positional notation uses positions for each power of 10, units, tens, hundreds, thousands, etc. The position of each digit within a number denotes the multiplier multiplied with that digit. Each position has a value 10 times that of the position to its right. There were at least 2 presumably independent sources of positional decimal systems in ancient civilization: the Chinese counting rod system and the Hindu-Arabic numeral system. 10 is the number which is the count of fingers and thumbs on both hands. The English word digit, as well as its translation in many languages, is also the anatomical term for fingers and toes. In English, decimal means tenth, decimate means reduced by a tenth, and denary means the unit of 10. The symbols for the digits in common use around the globe today are called Arabic numerals by Europeans and Indian numerals by Arabs, the two groups' terms both referring to the culture from which they learned the system. However, the symbols used in different areas are not identical. For instance, Western Arabic numerals differ from the forms used by other Arab cultures. Decimal fractions. A decimal fraction is a fraction the denominator of which is a power of 10. Decimal fractions are commonly expressed in decimal notation rather than fraction notation by discarding the denominator and inserting the decimal separator into the numerator at the position from the right corresponding to the power of 10 of the denominator and filling the gap with leading zeros if needed. E.g., decimal fractions 8 tenths, 1489 100ths, 24 100,000ths, and 58,910 thousandths are expressed in decimal notation as 0.8, 14.89, 0.00024, 5.8900 respectively. In English-speaking, some Latin American and many Asian countries, A period or raised period is used as the decimal separator. In many other countries, particularly in Europe, a comma is used. The integer part, or integral part of a decimal number is the part to the left of the decimal separator. The part from the decimal separator to the right is the fractional part. It is usual for a decimal number that consists only of a fractional part to have a leading zero in its notation. This helps disambiguation between a decimal sign and other punctuation, and especially when the negative number sign is indicated. It helps visualize the sign of the numeral as a whole. Trailing zeros after the decimal point are not necessary, although in science, engineering and statistics they can be retained to indicate a required precision or to show a level of confidence in the accuracy of the number. Although 0.080 and 0.08 are numerically equal, in engineering 0.080 suggests a measurement with an error of up to 1 part in 2000, while 0.08 suggests a measurement with an error of up to 1 in 200. Other rational numbers: any rational number with a denominator whose only prime factors are 2 or the fifth of may be precisely expressed as a decimal fraction and has a finite decimal expansion. 1/2 equals 0.51 20th equals 0.051 fifth equals 0.21 50th equals 0.021 quarter equals 0.251 40th equals 0.0251 25th equals 0.0418 eighth equals 0.1251 125th equals 0.0081 tenth equals 0.1. If a fully reduced rational number's denominator has any prime factors other than 2 or 5, it cannot be expressed as a finite decimal fraction, and has a unique eventually repeating infinite decimal expansion. 1/3 equals 0.333333. 1/9 equals 0.111111. 100 minus 1 equals 99 equals 9 times 11. 1/11 equals 0.090909. 1000 minus 1 equals 9 times 111 equals 27 times 37. 1/27 equals 0.037037037. 1/37 equals 0.027027027. 1/111 equals 0.009009009. Also, 1/81 equals 0.0123456799012. That a rational number must have a finite or recurring decimal expansion can be seen to be a consequence of the long division algorithm, in that there are at most q-1 possible non-zero remainders on division by q, so that the recurring pattern will have a period less than q. For instance, to find 3/7 by long division, 0.4285714 3.00000002830 divided by 7 equals 4 with a remainder of 2.2014. 20 divided by 7 equals 2 with a remainder of 6.605. 6.60 divided by 7 equals 8 with the remainder of 4.4035. 40 divided by 7 equals 5 with a remainder of 5.5049. 50 divided by 7 equals 7 with a remainder of 1.10. 10 divided by 7 equals 1 with a remainder of 3.3028. 30 divided by 7 equals 4 with a remainder of 2.20, etc. The converse to this observation is that every recurring decimal represents a rational number pq. This is a consequence of the fact that the recurring part of a decimal representation is, in fact, an infinite geometric series which will sum to a rational number. For instance, real numbers: every real number has a decimal representation, i.e., it can be written as where sign plus, minus, which is related to the sign function. Z is the set of all integers, and I, 0, 1, 9, for all I z to its decimal digits, equal to 0 for all I greater than some number. Such a sum converges as more and more negative values of I are included, even if there are infinitely many non-zero I. Rational numbers with prime factors in the denominator other than 2 and 5 have a unique recurring decimal representation. Non-uniqueness of decimal representation. Consider those rational numbers which have only the factors 2 and 5 in the denominator, i.e., which can be written as P2A5B. In this case there is a terminating decimal representation. For instance, 1 over 1 equals 1, 1/2 equals 0.5, 3/5 equals 0.6, 3/25 equals 0.12, and 1306, 1250 equals 1.0448. Such numbers are the only real numbers which do not have a unique decimal representation, as they can also be written as a representation that has a recurring 9. For instance, 1 equals 0.999999, 1/2 equals 0.499999, etc. The number 0 equals 0 over 1 is special in that it has no representation with recurring 9. This leaves the irrational numbers. They also have unique infinite decimal representations, and can be characterized as the numbers whose decimal representations neither terminate nor recur. So in general the decimal representation is unique, if one excludes representations that end in a recurring 9. The same trichotomy holds for other base n positional numeral systems. Terminating representation. Rational where the denominator divides sum and k. Recurring representation. Other rational. Non-terminating, non-recurring representation. Irrational. A version of this even holds for irrational base numeration systems, such as golden mean base representation. Decimal computation. Decimal computation was carried out in ancient times in many ways, typically in rod calculus, with decimal multiplication table used in ancient China and with sand tables in India and Middle East, or with a variety of abacus. Modern computer hardware and software systems commonly use a binary representation internally. For external use by computer specialists, this binary representation is sometimes presented in the related octal or hexadecimal systems. For most purposes, however, binary values are converted to or from the equivalent decimal values for presentation to or input from humans. Computer programs express literals in decimal by default. Both computer hardware and software also use internal representations, which are effectively decimal for storing decimal values and doing arithmetic. Often this arithmetic is done on data which are encoded using some variant of binary coded decimal, especially in database implementations. But there are other decimal representations in use. Decimal arithmetic is used in computers so that decimal fractional results can be computed exactly, which is not possible using a binary fractional representation. This is often important for financial and other calculations. History. Many ancient cultures calculated with numerals based on 10 Egyptian hieroglyphs, in evidence since around 3000 BC, used a purely decimal system, just as the Cretan hieroglyphs of the Minoans, whose numerals are closely based on the Egyptian model. The decimal system was handed down to the consecutive Bronze Age cultures of Greece, including Linear A and Linear B. The number system of classical Greece also used powers of 10, including, like the Roman numerals did, an intermediate base of 5. Notably, the polymath Archimedes invented a decimal positional system in his sand reckoner which was based on 108 and later led the German mathematician Carl Friedrich Gauss to lament what heights science would have already reached in his days if Archimedes had fully realized the potential of his ingenious discovery. The Hittites' hieroglyphs, just like the Egyptian and early numerals in Greece, was strictly decimal. The Egyptian hieratic numerals, the Greek alphabet numerals, the Hebrew alphabet numerals, the Roman numerals, the Chinese numerals and early Indian Brahma numerals are all non-positional decimal systems, and required large numbers of symbols. For instance, Egyptian numerals used different symbols for 10, 20, to 90, 100, 200 to 900, 1000, 2000, 3000, 4000, to 10,000. The world's earliest positional decimal system was the Chinese rod calculus. History of decimal fractions. According to Joseph Needham and Lamley Yong, decimal fractions were first developed and used by the Chinese in the 1st century BC, and then spread to the Middle East and from there to Europe. The written Chinese decimal fractions were non-positional. However, counting rod fractions were positional. Qin Jiushao, in his book Mathematical Treatise in 9 sections, denoted 0.96644 by, meaning 0.96644. The Jewish mathematician Emanuel Bonfils invented decimal fractions around 1350, anticipating Simon Stevin, but did not develop any notation to represent them. The Persian mathematician Jamshid al-Kashi claimed to have discovered decimal fractions himself in the 15th century, though J. Leonard Berggren notes that positional decimal fractions were used 5 centuries before him by Arab mathematician Abul Hasan al-Uqlidisi. As early as the 10th century, al-Khwarizmi introduced fraction to Islamic countries. In the early 9th century, his fraction presentation was an exact copy of traditional Chinese mathematical fraction from the mathematical classic of Sunzi. This form of fraction, with numerator on top and denominator at bottom without a horizontal bar, was also used by 10th century Abul Hasan al-Uqlidisi and 15th century Jamshid al-Kashi's work, Arithmetic, a forerunner of modern European decimal notation, was introduced by Simon Stevin in the 16th century. Natural languages. The ingenious method of expressing every possible number using a set of 10 symbols emerged in India. Several Indian languages show a straightforward decimal system. Many Indo-Aryan and Dravidian languages have numbers between 10 and 20 expressed in a regular pattern of addition to 10. The Hungarian language also uses a straightforward decimal system. All numbers between 10 and 20 are formed regularly, as with those between 20 and 100. A straightforward decimal rank system with a word for each order, and in which 11 is expressed as 10-1 and 23 as 2-10-3, and 89,345 is expressed as 8-9-3-4-5 is found in Chinese, and in Vietnamese with a few irregularities. Japanese, Korean, and Thai have imported the Chinese decimal system. Many other languages with a decimal system have special words for the numbers between 10 and 20, and decades. For example, in English 11 is 11, not 10-1, or 1-teen. Incan languages such as Quechua and Aymara have an almost straightforward decimal system, in which 11 is expressed as 10 with 1 and 23 as 2-10 with 3. Some psychologists suggest irregularities of the English names of numerals may hinder children's counting ability. Other bases. Some cultures do, or did, use other bases of numbers. Pre-Columbian Mesoamerican cultures such as the Maya used a base 20 system. The Yuki language in California and the Pameen languages in Mexico have octal systems because the speakers count using the spaces between their fingers rather than the fingers themselves. The existence of a non-decimal base in the earliest traces of the Germanic languages is attested by the presence of words and glosses, meaning that the count is in decimal. Such would be expected if normal counting is not decimal, and unusual if it were. Where this counting system is known, it is based on the long hundred of 120 in number, and a long thousand of 1200 in number. The descriptions like long only appear after the small hundred of 100 in number appeared with the Christians. Gordon's Introduction to Old Norse p. 293 gives number names that belong to this system. An expression cognate to 180 is translated to 200, and the cognate to 200 is translated at 240. Goodare details the use of the long hundred in Scotland in the Middle Ages, giving examples, calculations where the carry implies IC as 120, etc. That the general population were not alarmed to encounter such numbers suggests common enough use. It is also possible to avoid hundred-like numbers by using intermediate units, such as stones and pounds, rather than a long count of pounds. Goodare gives examples of numbers like 7 score, where one avoids the hundred by using extended scores. There is also a paper by W.H. Stevenson on long hundred and its uses in England. Many or all of the Chumashan languages originally used a base 4 counting system, in which the names for numbers were structured according to multiples of 4 and 16. Many languages use quinary number systems, including Gumaj, Nungabayu, Kuan Kopan Nutan Saraveka. Of these, Gumaj is the only true 5 to 25 language known, in which 25 is the higher group of 5. Some Nigerians use duodecimal systems. So did some small communities in India and Nepal, as indicated by their languages. The Huli language of Papua New Guinea is reported to have base 15 numbers. Nu means 15, Nuiki means 15 times 2 equals 30, and Nui Nui means 15 times 15 equals 225. Ungu, also known as Kaklili, is reported to have base 24 numbers. Tokapu means 24, Tokapu Talu means 24 times 2 equals 48, and Tokapu means 24 times 24 equals 576. Gati is reported to have a base 32 number system with base 4 cycles. The Ndom language of Papua New Guinea is reported to have base 6 numerals. Mer means 6, Merenthef means 6 times 2 equals 12, Nif means 36, and Niff means 36 times 2 equals 72.